Hello and welcome to another tutorial. We are going to continue our discussion on garbage collector, and this is just a brief introduction. We're not going to dive deep, but I will finish this this topic, and then we will look at the finalized method and what it does. So an object is eligible for garbage collection when there are no more references to that object. And we said that typically references are created on the stack frame of a method, right? We create objects in a method. And then when that method call returns, obviously the stack frame of the method is destroyed. All the local variables on the stack frame are destroyed. That means if we create an object in a method, then after we come back from the method, we lose the reference to that particular object. Then the state or the data that that object holds becomes garbage. Now sometimes the fields of other methods or other classes become reference types, right? For example, here this variable is of type cat, and then when we for example call a constructor, we can actually initialize this variable by calling the new operator on one of the constructors of this type, right? And therefore a field, a non-static field of this class, holds a reference or a pointer to an object that holds some data, right? And this is a very typical thing, and we said that this is the concept of composition. So in object-oriented paradigm, we can either go inheritance route or composition route, and we said that the way we distinguish between these, or the way we choose, is whether when we talk about different objects or different types, whether is a relationship makes sense or has a relationship. For example, if a basically is a relationship holds, then the relation between our types is inheritance. One type has to extend another type. If has a relationship holds, then means this type holds. We should go composition, which means one of the fields, part of the state of this type, is another type or a reference or pointer to another type. For example, the car can have a battery, right? And battery could be another object. We can create a new class called battery. And a battery could have, for example, a double or a float for internal voltage or just voltage. We can just call it voltage, right? And then obviously we can have a public constructor, and then we can either have a default constructor or initialize it, right? Voltage, and then this dot voltage. And note that I'm using this because the practice of Java is that the local variables, we always choose exactly the same name as the fields or global variables of a class, and then we have to use the this pointer to distinguish between the fields of a class and the local variables. I said that there are some conventions that other people follow. For example, they use underscore for fields, for example, and I personally avoid this kind of conventions, right? So I just the best practice is still to use the same names and then use the this dot, so that it's very understandable to the compiler what's going on, which one is the global field, which one is the local. And obviously Eclipse's color coding is extremely helpful in this case. All the global variables of a class, which are called fields, are blue. Static ones are italicized, non-static are regular font, and then local variables of a method are brown, somehow brown. So it's very easy to distinguish between them. Now obviously if I remove this dot, then both of them become brown, and I immediately Eclipse immediately gives me a warning that the assignment of variable voltage has no effect because you're assigning it to itself, because both of them are referring to this local variable. And that's immediately I see that because the color of the variable changes. So definitely take advantage of a good IDE. So, and then a car can have a battery, right? So battery, battery. And this battery can have a volt. Right now, this is a variable. Note that we haven't created any objects, right? We have not created any object yet of type battery. We said that the only time that we create object when we call the new operator on a type and then pass parameters so that JVM knows which constructor to call. By itself, right now, this is a field, a variable. Every variable in Java has to have a type, therefore its name is type, which means this variable can only point to objects of this type. That's the whole meaning of the type of this variable, which is a reference type or a pointer type, right? And then we haven't called the new operator yet, but maybe in the constructor, for example, if we have a default constructor, no constructor, we can initialize that battery by calling the new operator on the battery, right? And then double voltage, let's say a typical car has a 12-volt voltage, right? So we can pass the float. Now we are actually creating the object, and this car, because the relation between car and battery has a relationship, we use composition, which means the state of the car hold the data of another type, which is battery, right? So battery is a pointer. Now when we create an instance of the car and this battery gets initialized by calling this constructor, now we have car that has another object inside of it. Now the question is, what happens when car is destroyed? The answer is if car is destroyed and then nobody else, basically if we lose a reference to an instance of the car and nobody is referencing that, then that car becomes garbage. And when the garbage collector kicks in, it's going to also call the claim these reference type objects. For example, battery is another object, right? Because when car is destroyed, its state is no longer needed, right? Every amount of data that it holds has to be destroyed. So it also involves this pointer. And then when this pointer is destroyed, then the garbage collector looks at the object that this pointer or reference was pointing to. If nobody else referencing that, then that battery object is also garbage because nobody else was referring to it. It's just this car, right? So let's see. And we saw that as an object is eligible for garbage collection when there are no more references to the object. References that are held in a variable are usually dropped when the variable goes out of the scope. Or you can explicitly drop an object reference by setting the value to the special value null. So this is another thing. Basically, null is a keyword in Java, which we looked at before, and we said that whenever you create an object here by default, this line for fields, because when a JVM loads a class file into memory, all the fields are going to get their default values, which is for reference type, it's null. So this line of code, explicitly setting equal to null and not saying anything are the same for fields. For local variables, it's not the case. Local variables are not default initialized by the compiler, right? So there's a difference in between that. I think at some point we looked at that. Let's see, where did we look at it? Let's go back to car, for example. We had the main method here. Now we see if I run this, this works fine. So let's see. I guess we need to recompile this later, so you can have a reference, set it to null, and then that means now that pointer is destroyed. That's we lose the reference to a particular object. Let me see. Let's create a new class. Let's say null demo, and let's have a main method. All right. So I'm going to create a new class here. Let's call this dummy class. All right. And okay, we shouldn't use round brackets. So this class doesn't have anything, and then we can create a object of this type. Now, first of all, I can declare a local variable of a particular type. Just declaring a local variable. Declaring a local variable of a type, dummy class DC1, right? We haven't created any object, we haven't allocated any memory. We're just saying that this variable is always during the lifetime of this variable, which is the scope of this, it's going to only point to these objects, to the objects of type dummy class. But then we can initialize it, DC new dummy class, right? That's it. And now we actually, JVM goes and actually allocates memory, and if this class holds some state, some data, it also initializes those. But at the moment this doesn't have any data, anything, so this works fine. So declaration and then initialization, right? But then we could do it in the same step, new dummy class. We've seen this before, that so you can either declare and later initialize, create the object, or you can directly declare and initialize. In C++, we saw this before. There is a difference. In Java, these two are basically equivalent. In C++, it's different. In C++, if you write a line like this, it actually calls the default constructor of this object and creates the object. So this line of code is not just declaring an object type, it actually calls the default constructor. But in Java, you're just declaring a variable. That's the first difference. The second difference is that this line of code in C++ calls the assignment operator, basically because this object has already been created using the default constructor of this class. So when you do this in C++, what happens here is that a temporary object is created, and then the assignment operator is invoked on this type to assign the right hand side to the left hand side. But in Java, it's not the case. Here we're just declaring a variable, and here we're just initializing it. We say that now this variable points to this object that we created, right? So there is a huge difference in meaning of these two lines between C++ and Java. So be very careful if you are also doing C++ coding or you come from the C++ world. In Java, this line of code doesn't create or doesn't call the default constructor of DC1. All right, in Java, this line of code, in one line we declare the variable, the type, and then we allocate the object, and this variable points to the object. This line is exactly equivalent to these two lines, right? In C++, this is basically this just calls the constructor, right? So the meaning of this line in Java and C++ is more or less the same. And we saw that in Java, if we say that dummy class DC3 equals DC1, this just copy by value, right? This is copy pointers or references by value. This has nothing to, which means now this variable which points to objects of this type is pointing to the same object in the memory as DC1. It's just the meaning. But in C++, this line has a very different meaning. This actually calls the copy constructor of this object, right? So again, in Java, there is no concept of copy constructor. So this line of code has a very different meaning between Java and C++. Again, be careful about that. Now, we said that you can get rid of a reference by setting it to null, explicitly to the null. So I can say DC1, DC3 equals to null. That's it. And this line compiles. It means now this reference is destroyed. It's not pointing to anything. But for this object, there is still another object that is pointing to this class, DC, this object that we created, which is DC1. So we can set DC1 to also null, right? Then if I run this code, everything works fine. There is no problem. But let's see what the finalize does. We saw that the finalize is supposed to be called. It's supposed to be called when GC, the garbage collector, runs and claims this, right? So, and we said that it's a protected method, so nobody can call it. For example, I have a reference to DC2, this pointer pointing to this object, but I cannot DC2 dot. These are the only methods that are available in the superclass of the dummy class type, which is object, right? And these are the public ones. So we don't access to the protected ones, right? Protectors are not public. ToString is public, but for example, clone or finalize, these are not visible. And if we see the compilation error, it says that the method finalized from type object is not visible. And visibility means access modifiers, right? And Eclipse puts a line on this method to emphasize that this has been finalized, so you shouldn't be using it. But just let's try to see what happens. So I'm going to go right click, source, override implement method, right? And then the only super type of this dummy class is the object. And we can, in fact, a subclass has access to the protected methods of a superclass. That's what we discussed. If a method is private, no subclass can access it, which means no subclass can override it. but I'm going to select that I want to override finalize. And the concept of override means we want to change the behavior of this method that the superclass defines in the subclass. We saw that the concept of overriding a method in the concept of implementing interfaces. But overriding a method from the superclass, it doesn't have to be an abstract method. With interfaces, we saw that they're always abstract and the subtype has to always override and implement them. But Finalize has a default implementation, right? And we saw that in the object class, Finalize, the default implementation is doing nothing, right? So default implementation of Finalized method is just does nothing, right? So you see by default Eclipse, when it overrides it, it calls the superclass Finalize, which doesn't do anything. It's just an empty body. Note that you cannot have no body because this is not a abstract method. So you should have a body, even an empty body. But first of all, I'm going to get rid of this this exception thing, and then I'm not going to call the finalize of the super type because the superclass doesn't do anything. So we're just going to do something like sysout calling finalize in a dummy class, right? All right, let's see. We know that, and I'm going to run this code. We know that at this line of code, when we set DC3 and DC1, they're supposed to both point to this object in the Java heap. But when these are null, means now nobody can reference this object anymore. So this object becomes garbage. But if I run this, you don't see the call to the finalize. So this finalize was never called. So at this line object 1 that we created, let's call this object 1, is garbage. Because nobody is referencing, these two references are destroyed. So we expect the garbage collector to kick in, but obviously the idea here is that garbage collector kicks in when JVM realizes that it needs more memory or the memory needs cleanup. So when you run this code, you basically see that we have lots of memory, and these objects, obviously they don't have that much state, so they don't take any memory. So JVM realizes that at this line of code, at the end of line 31, there's plenty of memory remained. There is no point to actually run garbage collection and trying to clean up the memory. There is no need. And what we can do, and we saw that before in the I believe the new operator class, we saw that you can explicitly call the GC, right? Runtime GC. So let's see. So we saw that the runtime class is a singleton class, okay? And then we say that runtime.gc. So we are explicitly asking the JVM to run a GC, and let's see what happens. Nothing happened, right? We ran the GC, but this object didn't do anything, right? The finalize apparently was not called. Now I'm going to let's see, let's put this runtime as a field and a static field, right? So that we can access it inside the main. So we are calling GC kind of everywhere. So here, here, and then here. Let's see what happens. And we don't see any print of the finalize, right? But let's see what happens if we say put this code in another method. So public static void, let's say test1, and then we're going to move all of this code into test1. And then what we know that let's remove all the comment out, all the other code. Basically what happens here is that right now we're creating this object, right? Allocating this object in this method. So this DC2 is a local variable that points to this object that we allocated. Note that there is no notion of local objects because there is one big Java heap, Java memory area. All the objects, regardless of where they were created, an object might be created in this method, another object might be created in another method. It doesn't matter. The state of the object is always stored on the Java heap. And Java heap is shared amongst everywhere, right? It's just one Java heap for JVM. So later you see that even multiple threads see the same Java heap. That's why some breaks condition might happen, right? So all the method. The thing here is that whether you have a valid pointer or a reference to that object or not. So you create this method creates this, and then it's on the Java heap. If in the main method I have a pointer or a reference to that object, I still can access it, right? So for example, at the end of the method we can return this reference, and therefore now in the main method we have a copy of that address of that memory location so that we can still access that. But at the moment, as soon as we hit the end of this method, the scope of this method, this reference is destroyed, and so nobody else can address or access this object, the state of this object. So this becomes a garbage in the Java heap, right? So let's run this. Nothing happens. Now at the end of the main, I'm going to obviously call test1, right? So I want to make sure that we create this object, this line gets executed, and then that object becomes garbage. But the finalize is still not called, which means garbage collector doesn't run. So let's run GC right after that object becomes garbage. So after the end of this line executes, that object has become garbage. So let's run this, and still nothing, which is very interesting. Let's try to look at basically another, for example, JDK 15. Let's see what happens there. Let's proceed, and now you see that it actually calls the finalize. So apparently in JDK 15, if you run this with JDK 15, it actually calls the finalize, even though JVM knows that this class didn't have any state, so there wasn't really that much memory occupied by this, right? So JDK 15 runtime.gc definitely calls this. JDK 16, if we run this with JDK 16, let's see, nothing. So JDK 16 doesn't call the GC. Apparently it probably does a better optimization or better understanding. Let's see JDK 17. Let's run this. It calls the finalize method. So it's interesting that the JDK 16 is not calling the finalize, which means it's not running the GC, even though we kind of explicitly ask for it. JDK 17, it apparently does call the finalize method, right? Now this time it didn't call it. Let's run it one more time. It didn't call it. Let's run it again. It didn't call it. So it's very interesting. So now let's give this class some state. So int x1 is 100, int x2 is 200, right? Let's see what happens now. Nothing again. Let's try to basically create lots of these objects. So for int I equals 0, I less than 20, I plus plus, we're going to call this class. So we create and actually let's just keep one field and then public dummy class, and then this dummy class gets x, this dot x1, and I don't need to use x x equals x1 equals x, right? And then in the dummy class with the state of x1 equals plus x1. So in the finalize method we do this. Let's add let's say this gets an int x, we pass this x here, and now here we pass I. So we keep track, we index the objects that we create. So this for loop runs this method gets executed some number of times, and then we create lots of objects, and as soon as we return in each iteration of the loop, that object becomes garbage. So let's run this. Still nothing, right? It's very interesting that let's create 2000 objects. Still nothing. Let's run the GC Actually, let's use the system.gc, although I believe these are basically the same thing. System.gc just calls the gc from runtime. So we can also use the system.gc. So still the finalized method is not called. I'm going to switch back to JDK 16, or actually 15, and let's save this, and then let's run this. Let's proceed. And as you can see, in JDK 15, apparently system.gc always runs the gc. And you see that first of all, we know that which object is cleaned up in the memory with the system.gc. So in JDK 15 always runs gc, and finalize is called. So it's kind of not deterministic in JDK 15, but apparently in 16 and 17, no, that's not the case. The reason is that they're always improving that. Another reason is there are various types. So there are several types of GCs available in JDKs. So from JDK 15, they introduce. So there is a called G1 GC, which is kind of the main one, right? There is also ZGC. They introduced this. This is zero pause time. This is very fast. And there is a Epsilon GC. This one doesn't do anything. Epsilon GC does not do GC. It's just a placeholder. But if you want to see the performance of your application without any garbage collector, you run the JVM by telling it that use Epsilon GC, right? So I'm going to go back to one thing that I want to show you. If I go back to preferences and then Java and then install JREs, I've set the default workspace JRE to JDK 15, and if I look at this, you see I'm asking it to Eclipse to always run JDK 15 with ZGC. That's why JDK 15 is actually calling the finalize, is running the basically the garbage collection deterministically every time I ask it. Now if I go back to JDK 16, for example, and then I run this, you see the finalize is not called because by default GC is the default GC is not the ZGC. So let's go back here. If I look at my JDK 16, look at I haven't set any default VM arguments. But we can set the VM arguments for a particular class, main method of a class here, right? In the run configuration for this null demo class. So I want to tell it use ZGC. Let's apply and then run. And now you see that the ZGC is actually deterministically runs the garbage collector. So apparently ZGC always runs GC when you call runtime.gc or system.gc, right? Apparently it always happens. And as you can see, there is a random order here. For example, the first call to the finalize is 6:30, and then 16:53, 17:62. Now let's do 10, for example. And as you can see, all of them are running, all of them are cleaned up, and you see there is 6, 9, and there is, I believe the reason is for the ZGC, zero GC, that runs the garbage collection is that it's very fast. Its pause time is almost negligible for your application. I think that's the reason it's running deterministically, because JVM knows that there is no overhead. But let's use, instead of ZGC, so the flag is this one, -XX plus use ZGC. If you tell the JVM at runtime that use the zero garbage collector, the ZGC. Now we can use G1 GC, for example, G1 GC. So let's go back to our run configuration, and instead of ZGC, we're going to say G1 GC. So -XX plus use G1 GC. Let's see how this works. Now G1 is not calling that. G1 is not calling the finalized methods, and We can check if we can ask JVM to print the log of GC, and the flag for that I believe is -XX plus log GC, or print GC, something like that. Let's try that. So I'm going back to ZGC, use ZGC because I know that it runs the garbage collector, -XX plus print GC, or log GC. Let's see if this works. Log GC could not be, so let's see, -XX colon log GC, or log GC. Let's see if this works. No. So in the next lecture I'll show you what the exact flag is, but we can check what the actual flag is by let's look at the terminal by actually looking at the JVM flags itself, right? So what we can do here, I can actually, let's open a terminal here in our project. Let's say we don't know, let's say we don't know a particular flag for JVM. We can look at all of the flags of JVM, right? JVM. So where am I here? I'm here, and then what I'm going to do on my path environment variable, which Java, I'm using JDK 15, right? So let's switch to JDK 17, basically library.java, Java virtual machines, JDK, I believe 17, and then contents, and then home, and then bin, and then Java, right? I'm running the Java executable from JDK 17, and then -XX PrintFlagsFinal, or plus. Let's add a plus here. And these are all the flags, and what we can do, actually right now they're on the command line, which is hard to read, but what we can do, we can use the streams of the console, save it to a file. Let's say JDK 17 or JVM 17 underscore flags.txt. So I'm telling it whatever is the output of this command, shove it into this file. All right, so let's see if we got the file. Yes, JVM 17 flags. So these are all the global flags, and what we want to look for GC, concurrent GC threads, and then disable explicit GC invokes. And by the way, there is another neat way, if you are familiar with the bash terminal, is I want to say after you execute this, get the output, and then we're going to grep. Grep is another command line. So piping means feed the output to this other command line, grep GC, and then after that shove everything into JVM 17, let's say GC flags. All right, let's clear, and then now we have JVM 17 GC flags. So these are the flags that have this word capital G, capital C in them. And concurrent GC threads, disable explicit GC invokes as you can see, there's lots of flags, and these tell you what's the type: uint x, uint, unsigned integer, boolean flags are the ones that you set in your run configuration from plus minus. So you see this is a use GC is a boolean flag because it has a plus here. If I say minus use GC, it means don't use it, right? It's false. Plus means true. Let's don't save. So what we want is so you see there are some flags for the G1 GC, G1 mixed GC concurrent count target intervals, and then GC time limit. Again, these are very detailed. If you want to be familiar with, you have to learn a lot about GC to understand what these flags are. But there is one flag at the bottom is a boolean flag, which means you set it with plus or minus. Use ZGC. There is another one, use serial GC. There is another one, use Shenandoah GC. There is another one, use parallel GC, and then use G1 GC. So let's see how many. So apparently the GCs are enabled or disabled with the use keyword. So let's go back to our terminal. I want to say grep for GC and then grep it again for use. Okay. Let's see. All right, I think we overrode the previous one. So this is our GC flag, and then I want to say GC, instead of saying GC flag, GCs, right? All the GCs, all GC in JDK 17. Let's see which GCs garbage collector JDK 17 supports. I'm gonna search run all the flags of the JVM, grep or only filter the ones that have this GC word, and then of those grep again with the ones that have the word use in them. All right, so let's go down, and then now we have JVM 17 all GCs. Use adaptive size, decay, major GC, use adaptive size, but these are the ones, right? Use G1 GC, use so this is one. Let's close these, close these, close these, close these here. So JDK 17, it has use G1 GC, use parallel GC. It's a Boolean flag which you enable and disable it with plus sign, and then use serial GC, which is a old GC, right? And then it's a Boolean flag you enable and disable with a plus sign in your VM arguments, and then use Shenandoah GC. I believe this one was developed with IBM, and it's also supposed to be very fast, very small pause times, and then use ZGC. You might ask, where is the epsilon GC? It looks like there is no epsilon GC. But these are the actual algorithms, and we can try every one of them. So use G1 GC. So if I run this, okay, let's go back to our run configuration, and then let's run this. So we are running with ZGC. It definitely runs the garbage collection deterministically. Let's use G1 GC. It doesn't run the garbage collector deterministically. Use parallel GC. So let's see. Again, the plus means these are Boolean flags, which means we enable them, we set them to true. By default, these are false. We set them to true with the plus sign. Obviously, that -XX colon means we are setting a JVM flag. So parallel GC also is not calling the GC at this line. Let's look at the serial GC. It's not calling. Let's look at the Shenandoah. Again, Shenandoah and ZGC are very similar. They are supposed to be very fast, very low pause times. Let's run these. Use Shenandoah is not supported, which is very interesting because we saw, oh, we're running JDK 16. Okay, let's run JDK 17. So let's run this. Why is this not? That's very interesting. All right, I think the reason could be because Shenandoah is an experimental feature or something. So there should be another flag to unlock the experimental features. So let's see, unlock experimental. Looks like we can see we cannot search for it. So apparently Shenandoah is not supported in this one, which is very interesting, right? So I'm going to go back here and set this. So the default GC is ZGC. The default GC is actually G1 GC. So, but I prefer to use ZGC because it has faster or smaller pause times, and it kind of has a more deterministic behavior in terms of when you call the garbage collector, what happens, right? Now, another thing is about log. So let's search for log, for example, log GC. I believe we had one that had all the all GCs, GC flags. So adaptive size, G1 time, print GC. Okay, so print GC is the flag and it's a Boolean. So we set it to true or false with so we can say use ZGC hyphen XX colon plus, which means we're setting a Boolean flag to true, print GC. Now it also gives you a very interesting said at which time the GC was run. So at 4 millisecond, 12 millisecond, hyphen XX print GC is deprecated, hyphen X log GC. Okay, so we should use this one. So we should use hyphen X log. This enables the logging mechanisms of JVM, and GC, which means log GC activity. All right, so at 14 millisecond info GC using the Z garbage collector, and then GC index 0, which means this is the first time GC was run. Garbage collection through system.gc. It's very interesting that it tells you why the garbage collection was run. We explicitly called the system.gc, and it tells you we had virtually 0% of the initial memory used, but we had 6 meg, and now we have 4 meg, so we freed up 2 meg, right? So there is another one, print GC details. Let's see what this does. So this more is about the internals of the GC, like the algorithm and e-uses, etc. So as you can see, if we say print GC, it gives all the details of what's actually happening in the GC: concurrent selection, relocation, pause relocation. We have a pause time whenever the GC is run. Again, these are the details. I don't want to go into details, but JVM actually allows you to understand all the details. You can log them. You can see what's going on internally if you think that JVM was doing something not right. And Z heap, this is the initial heap, and we saw this when we look at the max memory initial memories. We saw that usually JVM initially requests 256 on a 64-bit platform, and the maximum is 4 gig. If you run a JVM in a 32-bit, if you request, so for a 64-bit, the max memory is capped at 4G and 4 gigabyte, and you can manually or explicitly ask JVM to basically override this. So the max capacity is 4G, the mean capacity is 8 meg, so it's really set to 8 meg, and it says that we used 8 meg. Meta space is the space I mentioned, all the static variables, all the when a JVM loads a class into the memory, all those stuff in addition to the static variables, the values that the static variables hold, they're all stored in the meta space. 134 kilobyte committed, reserved. Class space is how much space the classes that we created, right? The classes that we loaded into the memory are basically consuming. Now for the final example, I'm going to go back, and instead of ZGC, I'm going to use G1 GC, right? And we're logging the GC and print GC details. And as you can see, using G1 GC version this, and then what happens here is that the GC is actually run. So even if I don't call the system.gc, it prints the GC, right? But you don't see GC bracket 0, which means GC didn't run. However, when I call this, you see this line, which means system.gc, even with JDK 1617, right? JDK, it actually calls the GC, but the thing here is that it doesn't call the finalized method anymore. So that's the final point that I wanted to make, right? GC 0 means the GC is actually running. So version 17, memory large, and then compress oops enables, which means the JVM is starting with a 32-bit reference types instead of 64-bit. Max capacity, initial capacity, mean capacity is 8, initial capacity 256, max capacity is 4G, and the GC was run, GC pause full, and that's because it says that system.gc was called, so we are running these. And then phase 1, phase 2, these are different phases of the garbage collection algorithm. And then it gives you some status, right? So the GC is running, but from JDK 16 or 17, so from one of these, so up to JDK 15, finalized method is called by GC. But from JDK 16, I believe the finalized method is not being called anymore. So let's set to JDK 16 and run. Yes, so we don't see the so it tells us we're running with JDK 16, but we don't see the prints of the finalized method. The GC is still being called, right? We have one GC, GC 0. This is index 0, means this is the first time the GC is called. Now what happens if we run the GC again? So let's see. And now we have GC 0, which means this is the first time GC was called, and then GC 1, this is the second time. So this number inside is the index, how many times the GC is called. And then the finalize is not being called. So up to JDK 15, finalize method is called. From JDK 16 and onward, finalize method is not called anymore, which is very interesting, right? So I hope you enjoyed this lecture. Now have a very solid understanding of the JVM flags and then GC flags and which garbage collectors your JVM supports. You can see all of them. In order to enable a particular garbage collector, there are Boolean flags. So you use -XX plus or minus, depending on either plus, for example, use ZGC, or -XX minus, use ZGC. Plus means set this Boolean flag to true. Minus means set this Boolean flag to false, right? So I hope you enjoyed this. Please stay tuned, and I'll see you in the next one.